So welcome. This is the 8th review session, I believe. Okay? So this is an important one. This is just before the exam next week. So who wants to try problem number 1? Can I have apples as usual? We'll work through all of these problems. The goal is you guys try it and then I help you guys through it, okay? Somebody wants to try. No? You want to try?
I do not know how to do it. If someone does, we should.
Does anybody know how to do it?
I'm happy to do it and we can work through it.
Okay, that's fine. Anybody else want to try? Because we'll give it to Caroline. All right? Try. I'll give you support, okay? Let's see.
That's exactly what I'm doing, and I haven't had dinner yet.
So this is a multi-stage problem, okay? Because first you need to draw the structure of this S4-iodo-2-methyl-hexane, okay? So you draw hexane, 1, 2, 3, 4, 5, 6, okay?
Mm-hmm.
And then in the 2 position you put a methyl, in the 4 position you put a...
And then do I need to show that it's a chiral center, like put one
Yes,
in?
you need, but put the iodo first.
Mm-hmm.
So doesn't forget it. So 4 iodo.
Okay. So, okay, here we go.
Okay, so that's without stereochemistry. Then the next thing is you want to draw it with either as R or S, right, with the stereochemistry.
Mm-hmm.
So the way I do it is generally I just draw it, let's say the iodo coming forward,
Mm-hmm.
randomly, and then I check whether it's now R or S, and if it's S, then you draw it backwards. You know,
Okay.
or if it's R, then you draw it backwards, because you want the S.
Okay, so I will do that.
Coming out.
And I feel like it's the opposite.
So let's see, let's assign RS.
Okay.
So maybe you can talk people through how to do it again.
Yeah, so this is A. This one's going to be B, C,
So you guessed correctly.
and so this is an S. So we need to switch it.
No, we won't.
No, it's good.
Oh, sorry.
We won't.
You've got
So
it.
it's good.
Yeah,
Perfect.
okay, cool.
Okay, so that's the part number 1. Okay,
Mhm.
great.
Check.
Now we need to figure out what reaction is going to happen. Okay.
Okay.
So since we are in chapter 7, what do you think happens? Either SN2, SN1, E2, or E1. You have 25% chance. So what do? You look at the substrate first, and you look at what reagent you have. So is there, and we'll go over this more on Friday. I'll give you a table on how to do this, but for now, you basically look at this. What's the reagent? Sodium SCH3.
So it's strong. It has a negative charge.
It's a negative charge. What did I say about sulfur?
It's a strong base.
No,
No.
strong nucleophile.
Strong nucleophile. Okay.
Nucleophile. Sulfur is very polarizable. Oxygen is usually more basic than sulfur. Remember, sulfur SH is like an SH bond is more acidic than an OH bond. That means SH is S minus is a weaker base than O minus. Okay, so it's not S minus. It's not very basic.
Okay.
S minus is a great nucleophile because it has polarizable orbitals. Okay, so this is a great nucleophile. So what will it do? Great nucleophiles tend to be involved in which kind of reaction?
Substitution.
Substitution. SN1 or SN2?
SN2.
SN2, right? Because the nucleophile is involved in the reaction, it actively participates in the reaction. It's a bimolecular mechanism. So now this stuff.
I can just draw a new one. I don't know how to erase.
Draw it on the right again. Don't erase the old one. Just redraw it so we don't have too many A, B, C, Ds in there. I think that will help. But essentially, we are narrowing down towards SN2, okay?
Mm-hmm.
Does it fit with the substrate? It's a secondary alkyl halide, right? It's kind of in between. You can do SN2 or SN1 or elimination. But the nucleophile here is the determining factor because you have a great nucleophile will do SN2 reaction. Okay? So, can you draw the mechanism? So draw an S. No. Oh, okay, keep going.
Mm-hmm.
First of all, can you pick red? Can
Yes.
you undo it and then pick red for the arrows?
Whoop.
Whoa.
No, that
Where
is
it?
not.
You
what
pick
we-
that one, yeah.
Oh, there you go.
Okay.
There we go. Just click on anywhere on the thing. Perfect.
Okay, and then
Perfect. So it's concerted, right? Now, from which side is the sulfur coming? Is it coming from the front or from the back?
Back.
From the back.
From the back, right? And you get inversion of configuration, remember? So then you can draw the product. Perfect. Perfect. That's correct. That's it.
Okay.
Thank you. I got you an apple. Okay.
Whoops.
Don't worry.
Oh my
Apple product. It should be pretty stable, hopefully. We'll see. I heard you guys talking about apples, so I thought you guys were big fans of apple. And I have apples. Okay. All fits together. Okay. Oh, good. Okay. So, any questions about this problem? Yes? Can you let me come to you so that people can hear what you are asking. Okay?
How do you know if the nucleophile is going to attack the front or the back?
Okay. Question is, how do we know whether the nucleophile is going to attack the front or the back? It's always going to attack from the back side of the carbon-iodine bond or of the CX bond. Always.
So does that always result in an inversion?
It always results in inversion of configuration. That's what we said about SN2 reactions. But that's only the case if you have an SN2 reaction. If you have an SN1 reaction, it's not the case. Okay? We had another question. Yes?
So the other product would be the iodine. So that would have the negative charge on it. So where on this is the positive charge? Because they have to balance, right?
Say again. So yeah, the other product, we can draw it. Actually, you're right. So it will be plus I minus, right?
So then what has a plus on this side to balance it out, since on that side it was neutral?
Oh, the question is what has a plus to balance it out. No, well, it depends. If you include, so actually, what the reaction we drew, right? You can, if you draw it without the sodium, it's like this,
Okay.
and then it's negative on the left side. You see, to start with on the starting material side, because you have the overall charge -1. Now, if you include the sodium, then that's what balances the charge, and that will still be present on the right.
Okay.
But then the sodium is, as we said in lecture, it's just a spectator ion, right? So you can either put it on both sides to balance the charge, or you don't put it, that's fine. All right? Okay, let's move on to the next question. Okay, what is the product of this elimination? And then what happens if you would use T-butoxide instead as the base? So it's a two-part question. You guys want to try?
I'll try.
Good.
Okay.
Keep talking a little bit while you are doing the problem so that
Okay.
you can follow.
So this is a pretty strong base.
Yes.
So that means that we're going to have an E2 reaction.
Yes. E2 reaction.
So that means that it's concerted. It's all going to happen at once.
Uh-huh.
So you got this little H back here doing its own thing. And then you start doing your drawings. Oh, here we go. That's what I want. Sorry. Just changing the color. And what happens is that this goes here, and this pair of electrons on the O will go up and attack this H, and then the bond from the H comes here.
Okay, so you make a double bond. All right?
Yeah, so this is
now
your...
the question is, how do you know that it's taking off that H and not the H over here? I'll show you on the screen. How do we know it's not taking off one of the H's over here? Double bond here?
Because making the double bond in the center right there stabilizes it better.
Okay, and we have a small, like non-sterically hindered base.
Right.
So it makes the so-called Zaitsev product. Remember we talked about the Zaitsev versus Hoffman product? So when you have a smaller base, it makes the Zaitsev product, which is the more substituted one. Yes?
Is this one has to be very rare combination to like these
Yes. So now here we go, all right? So that's part one of the problem. So what you drew here, let me see. I'll show you on the screen. No, that's fine. It's fine. It's good. We're starting off pretty good. Okay. So we are making the Zaitsev product. Now, what is not perfectly correct here is look at this carbon atom here. How you draw it. you have this part here coming out of the plane.
Oh, but I need
Right.
to draw it.
But what is the S hybridization here on this carbon?
SP3.
No, sp2.
It's a,
So this is it started as sp3 over here, right? But then we lost we made a double bond, so now it's sp2 over here. So it needs to go straight. It can't come out of the plane because otherwise, if it's like the way it's drawn, it's kind of like it would basically be tetrahedral, you know, or it's like it would be, you know, what I mean, it needs to be trigonal planes. It needs to be all in the plane. So one possibility for the product would be to basically do this and take this off and say, all right, we go straight up, right? But now what's the other possible product which can form? Well, yeah. So you could form. So this is the Zaitsev product. Okay, that's the favored one. No, but the other product you can form. Look, this is what the one you just drew is the E. That's the E product. The possibilities you could potentially also form the Zaitsev Z product. Okay. But now the thing is only one of them can form because you see you only have one beta hydrogen here you're taking off. So it's a stereo-specific reaction. So the question is, do we form the one on the left or the one on the right? And so what we have to do is we have to take the starting material, rotate it so that the bromine, the carbon-bromine bond and the CH bond, they're anti-periplanar to each other. And then we need to eliminate. And then we figure out whether we form the E or the Z product. You see what I mean? So we kind of are done halfway with the question. Does it make sense? So we can continue. So I'm going to give it back to you. I'm going to take these off, and then let's draw it as an anti-periplanar conformation. We do it together, okay? We are on the right pathway.
I'm sorry.
Huh?
I said sorry.
It's perfectly fine. Keep going, okay? This is hard. That's the hardest thing. I'm telling you. I told you in lecture, this stuff is hard. It's the real deal of organic chemistry. Don't worry about it. We'll figure it out, okay?
Okay.
This is a hard problem. This is one of the hardest ones I've put ever on an exam, okay? This
Why
is
did
like
I
the
choose
end
to
goal.
do this?
But I think, if we do these review sessions, you might as well do hard problems so you really get the whole thing, So you don't just see it for the first time on, on the exam. All right? This is a hard problems. Okay?
I want these to be
So we rotate it. All right? The easiest thing to do, let's see.
That's just me rotating it. This isn't the product.
Okay, so what did you do? You rotated the right side here, right? Let me think.
I have no idea what I'm doing. That makes him think this hard.
Wait, doesn't it flip? Let's see. What do you guys think? So you rotate around this bond, right? So and the bromine initially starts to point back. So you rotate it until the methyl,
So my BR is coming out.
The BR is coming out, right?
There we go. There we go. Nice and pretty now.
But then, hold on. You don't want the BR to come out.
Because it's not anti-periplanar
It's
then.
an anti-periplanar.
Joke's
So you
on
want to
me.
rotate it more. So you make a line there, okay?
I
Now
am-
the only question is the methyl coming out. Yes, exactly. That's how it is. Alright? So your modeling kits will probably help with this. You need to get your modeling kits on the exam and you figure out how it's oriented. And then you rotate it around that bond so it's anti-periplanar, okay? Make sense?
Okay, so then my product I end
So
up.
how can you check whether you're rotating
Oh.
it correctly? Modeling kit, if you don't have a modeling kit, you can do RS for this stereocent and see if it's still RS on it. Okay? So priority 1 would be the bromine, priority 2 would be this, priority 3 would be this. So this is what, S. Okay? What about here? Hydrogen is coming forward, bromine priority 1, 2, 3.
But then you gotta flip.
What?
You gotta flip them.
Oh, we flipped it?
No, I'm just talking to myself, really. But they're the same stereochemistry. So is that right?
Let's see. That's the question. Are they the same stereochemistry? Let's assign it. Are you sure? Yeah. Let's see. The H is coming forward. This is 1, 2, 3. So this would be R, but it's coming forward, so it's S. Okay? And this one we just assigned as S. Did we? So
yeah.
These are the same. Does it make sense?
That was my pen cap.
All right? Yes.
I still don't understand, like, I thought they're supposed to be, like, anti-coplanar. The ER.
They're not anti-coperiplanar yet.
Yeah, okay. Oh, okay, good.
We just rotated the right side to put the carbon-bromine bond into the plane. Now we have to rotate the left side.
Oh no.
Okay.
Because you see the bromine and the CH, they are not yet anti-periplanar. Alright? So keep rotating the right side.
I don't know how.
You just like take this part and you just like rotate it.
I know that, but I don't know what. Here, I'm giving up on this question.
Okay, let me do it, okay? You watch me do it.
Okay.
Let's see. So this is good. Now we look at this bond here, this part, okay? What we have to do is we have to rotate it like this. All right, so that the hydrogen starts to be in this position here. Does it make sense? Let me show you. So we go, and the right part we write as the same. So we say this is the same as a thing where, so the right part, I'm just rewriting this, okay? The right part. Now the left part, we want the hydrogen to be down here. Because then the hydrogen, you see, let me highlight it. The hydrogen, the CH bond, which you're taking off, and the carbon-bromine bond, they're now anti-periplanar. You see that? So you want to rotate it down there. Now you want to make sure. Now you do that, okay? What happens is this methyl group here will point to the front or to the back? To the back, kind of like when we did the Fisher projections, right? We're just turning it around. So this is pointing to the back, okay? That's the methyl. And then the other group, this part, will point to the front. You guys see that? Like this. So that's the yellow group.
Okay.
All right? Now we rotated it. And now, I'll show you a trick in the future, okay, in a second. But I want to make sure you understand how I'm doing this stuff. Okay, now we can do the elimination. See, now it's anti-periplanar. Okay? So now we take the base, comes in, kicks it out. And now we get, what do we get? The E or the C product. Remember, there is, what's pointing back here is a hydrogen. Okay? There's a hydrogen there. So that means when we draw the product, you see the hydrogen and the methyl group are on the same side. So they are both going to end up on the same side in the olefin. And the other two parts, I mean the hydrogen, what I mean is this hydrogen and this methyl group. They're on the same side. Okay? So now you end up with this product, which is the Z product. I see you guys are all excited about this stuff. Okay? It's a C product. Does it make sense? So, I'll come to your question in a second. Now the... Yeah, that's how it goes. I think. That's how you have to do it. So there's tricks to it. You can, for example, you can take this starting material here. You don't necessarily have to rotate it all into one plane. You know, you could just rotate the left side and leave the right side alone, realizing that the carbon-bromine bond is kind of pointing back. down and backwards. Okay, so you can do that. The other way to do it, which might be easier for you guys, frankly, is to do a Newman projection. Okay, so let me show you how it goes with a Newman projection. Just for the sake of doing it. All right, Isaac, I will come to you in a second. Okay, so what you can do is you say, all right, we need to rotate around this bond here. So we're going to look at it, for example, from this side. Okay, drawing the hydrogen might help you. Okay, and now we're going to start to draw a Newman projection. So you're like, all right, what's in the front? We have a methyl pointing straight up, bromine pointing down to the right, okay, and hydrogen pointing left. All right, now, what else? In the back, what do we have in the back? We have a hydrogen pointing up and to the right, an ethyl pointing like this, up and to the left, and sorry, that's wrong. That's wrong. The methyl is pointing there, right? Up and to the left, and the ethyl is pointing down. All right? Now, once you have the Newman projection, I think it is easier to rotate. That's the advantage of the Newman projection. All right? So you see what you want now is this is the carbon-bromine bond, and this is the carbon-hydrogen bond. And you see how they're gauche to each other? All right? They're like gauche. They're next to each other. So you want to rotate, for example, just the back wheel so that it ends up to be anti-periplanar, those two bonds. All right? So what I'm going to do is I'm going to shrink the right side here so that we get some space. And we'll see if we end up with the Z product as well, all right? So I'm just going to put a divide here. All right? It's just an alternative way of solving the question, all right? Might be easier for you guys. So we rotate the wheel. We rotate the back wheel. We leave the front wheel alone, for instance. So you can rotate the front wheel, leave the back wheel alone. Doesn't matter, okay? But we rotate. And so we redraw the front. We don't do anything to it. We just leave it as it is. All right, here we go. And the back we rotate so that the hydrogen now ends up over here. Okay? So what we do, we rotate by 120 degrees, right? Counterclockwise, the back wheel. That means, let's see, the methyl group ends up here, the ethyl ends up here. All right? Now we eliminate. So what's going to go away are these guys here. So we eliminate. I'll just say E2. Now the E2 reaction happens. And so what ends up on the same side, look, is this methyl and ethyl. They and the methyl and the hydrogen here. They are on the same side. Right? So they end up on the same side in the olefin product. So you can draw a Newman projection of the olefin. Which looks like this. Now the olefin is trigonal planar, right? So if you look at it along the double bond, it looks like this. It looks like this. You have in the front, you have methyl and hydrogen. All right? And in the back, we have ethyl and methyl. You guys see that? And that's the same as that's the same as that's the Z product. Okay? You see, I'm going to highlight these two parts. So let's see, I'll make this in, the ethyl is here. Right? That's the ethyl. And the methyl is here in red. Okay? So that's this methyl. And you see they're on the same side. And on the other side, in orange here, we have the methyl and the hydrogen. And that's the hydrogen and the methyl over here. Does it make sense? So you see, you can do it either with the Newman projection, or you can do it with the other way. Or what you could also do is you could take this thing as the Newman projection, and then redraw it as a normal molecule, like as a zigzag drawing, and then eliminate it, if that helps you. I think the easiest way probably to do is with a model kit. Okay? Questions? Yeah.
When you rotated it, how did you know which way to rotate it and how many degrees to rotate it?
You just imagine. Like, oh no, so I knew, you see, this hydrogen
Yeah.
needs to end up here so
Yeah.
that it's...
How did you
I just-
know that it didn't need to go this way?
Oh, because it needs to be on opposite side of the carbon-bromine.
Okay.
Right? So if it's over here, you see the carbon-bromine is pointing
Yeah.
down to the right.
Okay.
So this has to point back to the, like up to the left.
Okay.
So it has to be opposite, it has to be anti.
Okay.
Okay? If you rotate it by, what is it, 180 degrees or something, if you rotate it too much, then it becomes, it's not anti anymore.
Mm-hmm.
There's only one way you can rotate it so it's anti.
Okay.
Okay? Good question. Yes?
Yeah, so with it being like, you're going for that hydrogen because it's on the beta carbon? Is it on the beta carbon?
Yes, it's on the beta carbon. Let me show you.
Okay.
Let's count the carbons, okay? That's the first step you have to do. You have to so this is the alpha carbon, right? Where the bromine is attached. And now the beta carbon is here and here. There's 2 beta carbons. So now we said we are going to take the more hindered beta carbon because it gives the more substituted olefin because it's a small base. Okay? Now the question is, what will happen if you take a more hindered base? Like T-butoxide. That's the next part. We are only halfway done with the question, remember? I'm going to give you guys some apples after, okay? So what do you think happens with a more hindered base now? It goes to the hydrogen on the other beta carbon because that's on a primary carbon atom, right? And that the hindered base can reach that better, as we said in lectures, gives the Hoffman product. And so that's what happens. Okay? So in this case, we'll just do this in green here. We'll say with, this will be quick. This is much easier now. Because it doesn't matter. You see now there's 3 hydrogens on that other beta carbon on the right, on that methyl group. It doesn't matter which one we take off. It's just going to make a double bond. It doesn't matter whether it's E or Z, so you don't have to worry about it. It's not stereoselective. Okay? Or stereo-specific. So let's do this. So with T-butoxide as the base, here's what we get. Okay? We basically take our starting material. I'll just keep drawing in green. All right? Here we go. This is our starting material. And there we go. That's the bromine. All right? And now we're going to take off one of these hydrogens. Okay, so this is the T-butoxide, and it's coming, and it's taking off one of these hydrogens, and you don't have to worry about which exact hydrogen is anti-periplanar, because all you get now is the product, which looks like this. Like this part is all the same. It's unaffected. And here we go, and we get the double bond here. See, it doesn't matter whether it's E or Z here, so it's easy. It's easier, you don't have to worry about the anti-periplanar stuff.
Okay, so what's the
question?
the point of the anti-periplanar? Like,
What's the point of the anti-periplanar? Why does it matter in the other case? Because if you didn't know about the anti-periplanar, you could form either the Z or the E olefin product.
Okay, so you want to figure out whether it's...
You want to form whether it's the Z or the E in this case. And that's why you have to go through this anti-periplanar kind of analysis, which is really a pain.
So there's 2 different products that can form with the first one, which is why you
Yes.
get the anti-periplanar.
Yes.
But the second one, there's not 2 different products.
Yes, because there's no E or Z.
Okay.
You see, because you have 2 hydrogens attached here. So there's no E or Z. It doesn't matter which hydrogen you take off.
Right. Okay.
Okay? Does that make sense to you guys? Okay? I told you this stuff is hard, okay? Let's give you guys some apples. So stay with me. This might be a little bit of a longer review session, but I think that's fine. All right? Caroline, here.
Oh, thank you.
Apple. Oops, sorry.
I have another
Here.
question.
Oh, thank you.
I'll get you an apple.
That's okay. How do you?
Okay, one more question,
How do you
guys.
know that this one is going to do this, the Zysef, and this one's going to do Hoffman?
How do we know? Good question. How do we know that the methoxide is going to do the Zysef and the T-butoxide is going to do the Hoffman? Can somebody answer that? We talked about it in lecture. It has something to do with the size. So whenever you have a sterically hindered base, you form the Hoffman product. Whenever you have in an E2 elimination, whenever you have a not so hindered base, like methoxide, then it forms the Zysef product. That's the rule. So Zysef product, the more stable product, when you have with a smaller base, Hoffman product with a sterically hindered base. That's the rule. Learn it as a rule and apply it. Okay?
Hindered equals Hoffman.
Yes. Good question, okay? And so with T-butoxide, hindered, Hoffman. Methoxide or ethoxide, not hindered, Zaitsev. Okay? That's the rule. Just apply that rule. It's called the Zaitsev and Hoffman rule or whatever. Has something to do with because the hindered base can't reach the sterically hindered site. Okay? Any other questions? Sorry, Isaac, you had a question. Did we go over it? Okay. All right, let's move on. All right, we are moving. We're making progress here. Here. All right. So that's what's found experimentally. Okay. Does anybody want to try? So we have with this substrate, we have an E2 reaction which is really slow, and only one product is formed. You want to try it? Okay. So what I did is I drew it again here on the next slide, so we have some more space. Okay. I'll get it to you. Give it a shot.
All right.
Did anybody still get an apple? Earn an apple? I think I gave you guys an apple. Huh? Oh, you, yes. Sorry. You did like that problem. You did a pretty good job. You got like half of that.
All right.
That's like the hardest one on the whole problem set.
So for this one, I drew first the chair of the thing.
Good. That's exactly how you should get started. So you start to notice the cumulative nature of this course. So if you have trouble drawing chairs, then you are stuck. You know what I mean? So it's building up, okay? That's why it's a hard thing.
So
good.
The butyl group here, most of the time is going to want to be equatorial. So I need to find somewhere that's pointing up and equatorial. So it could just be like here.
Perfect.
And then the chlorine next to it, because it's trans, is then also going to be equatorial, which
down, right?
Is and down, and that's a problem for reacting because then the hydrogens next to it for the elimination are none of them are going to be in the right
None of them are anti-periplanar, right, or anti-coplanar. As we said in lecture 2, so the other thing is the chlorine is not. So maybe draw H there. Otherwise, it's like methyl, right? Remember, if you draw just a line, even if you mean H, it means methyl, right? Perfect. Yeah. So what we said in lecture is you have to flip it. You have to get it into a conformation where the chlorine or the CX bond is axial, right? As we discussed in lecture today. So how can you do that from here? You have to do a chair flip.
Yeah.
Right.
So you flip the chair.
So maybe draw an equilibrium arrow. To show that these two structures, those two flipped chairs, they're not the same structure, they're in equilibrium, right?
Okay, that's kind of
and it's favoring the left side.
Yeah.
Right? Yes, good.
So then now this is
is axial?
Axial, and then the chlorine is axial, which means that the chlorine can then do the reaction with this hydrogen here.
Yes.
So, and it's slow because this side doesn't want to form very much because of this big, the big tert-butyl group being axial, because that's really high energy.
Yes.
And then, and it would only form the one product with the...
So can you draw the product and even the mechanism?
Yeah.
Let me give you, we zoom out again. Okay. So maybe if you can, pick red.
Red.
So you just click on this guy and then pick red. Perfect. Okay. Just for the arrows. I like to use red for the arrows. Yeah. It's easier.
So
you can just start on the O here, the arrow for the elimination.
So the elimination is going to go like this. And then this thing goes here, and then that goes there.
Perfect. Start the second arrow on the CH bond, right? You're kind of starting it on. Remember we said on the electron pair. Otherwise, it's perfect. But you start it in the middle of the bond. Okay.
Yeah.
Okay. Perfect. Now all you have to do is draw the product for me.
And then the product is going to be.
So maybe pick red again, black again. Sorry.
Yeah. And then the product is going to be here, the one that.
So just draw a normal arrow. Yeah. Perfect. Yeah.
It's going to have this thing here. And a double bond.
Perfect.
There.
Perfect. That's it. That's absolutely correct. Are you willing to do the second part?
Yeah.
Sounds like you are on a pretty good move. So I'm gonna just. Any questions so far? You guys are good? Yeah. See, that's much easier already than the one. The one before was like the hardest. Okay. I told you guys in lecture the anti-periplanar stuff freaks me out. It's like really hard. Okay. That's the worst. The rest is not that bad. Okay. So let's continue here. Click on the next one. So this one forms two products, and the reaction, the E2 reaction, is fast now.
Yeah.
Right? So see if you can draw the chair and rationalize it. Okay?
Okay, so...
Same as the one before, it's just you have to kind of work for it. So that's the chair.
That's the chair. And then the T-butoxide... T-butyl, right, is pointing up.
It's up
and
and
then
it's equatorial.
Equatorial, because that's where it wants to be most of the time.
Uh-huh.
And then the CL is also pointing up. So now the CL is axial, which means that it is anti-coplanar with this hydrogen and this hydrogen.
Yes.
So it's fast because the favored chair conformation puts the chlorine in the axial position.
So it's pre-organized, you know, with the chlorine there to eliminate, yeah?
And then...
and there are two hydrogens you can take off. They're both readily available in the anti-coplanar conformation, right? So just draw the arrows for both. Maybe pick red for one of them.
So it can go to this one.
Yes.
And
so finish the arrows. Let's just finish the arrow for this one.
Yeah.
You know, and then we'll pick another color and draw the other possible.
And
like
be
this.
Like that. Yeah. Or it
can you draw the product? Let's just draw it in red, maybe.
Yeah. Okay.
For this one, the product for this one?
For this one, the product is going to be... I could be lazy and just draw...
Oh, yeah, just circle. Yeah, that's perfect. That's absolutely great.
And then the other one...
Maybe pick like green or any other color. Yeah.
The other one would go for this hydrogen, because now the hydrogen next to the T-butyl is in line 2, unlike the other one. So that can go here, and then it's the same thing, and that forms this second product.
So I will let you teach the course next year. No, this is great. This is awesome. All right. Do you guys have any questions? It's a beautiful problem which connects like reaction rates and how many products you can form and how fast it goes, you know, with everything, with chair conformations and everything. Okay, very good. All right, thank you so much. Appreciate it. Any questions? Yes.
So the number of products that can form is related to how many are available in the anti-periplanar.
Yes.
Okay. So
Yes.
since there's 2 here, there's 2.
Yes. It was like in the linear case, right? If we had 2 beta hydrogens, which can be anti-periplanar, then you get a stereoselective reaction. Then you can get either the E product or the Z product, right? Or you can get the Zaitsev or the Hoffman product, depending on, you know.
Right.
So that, but if only 1 beta hydrogen is available, then you can only take off that one in the anti-periplanar conformation.
Gotcha.
Then there's only one. So the anti-periplanar thing is a good thing to think about. Okay, it always has an influence. We'll go to maybe you first, and then to.
Mine's quick. Why is the terp-butyl coming out of this page and not out of this one?
Oh, good question. Why is the terp-butyl drawn? You know, here it's coming out, here it's like not coming out. Because of the hybridization. You see, here there is a hydrogen attached. Here it's sp2. All right, that's why. Does that answer it?
Yes.
It's a good question. So you have to be very careful about that. Right? So let's say if you draw this product with it coming out like this, I will take off at least the point. Oh, not me, the TA. So maybe I'll give you the point back or something, but maybe not. Okay? Does it make sense? You have to pay attention to the hybridization. Sometimes if you're making a double bond that you eliminate, then you make it sp2. Then it's not coming out of the plane. All right? If it stays sp3, it stays like that. Isaac,
Is the compound on the right, the product on the right, is that the Zaitsev, the favored one?
Yes.
Yeah.
You're right. So the one actually on the left is the Hoffman product.
Okay.
The one on the right is the Zaitsev product. So how could you favor from, let's say you can form both with this mechanism. With methoxide, you kind of form both a little bit. Probably more, with methoxide, you probably form more of the Zaitsev one, right? Because it's the more stable product, absolutely. The one on the left, how can you form more on the one on the left? You can change the base.
Would you use a bigger, like the terp?
Yeah, so if you use the terp-butoxide, you get more of the left product, of the Hoffman product. Exactly right.
So they're not like racemic. They're not generated.
Oh, they're not generated the same. They're different compounds.
Totally, okay.
They're totally, they're actually, these are constitutional isomers. You see? These are constitutional isomers because the connectivity is different.
Okay.
These are not even stereoisomers, okay? Good question, very good question. Yes? Because, so when we look at, the question is why is the one on the left less stable than the one on the right? Because we said the more substituted an olefin is, the more stable it is. It's due to hyperconjugation, like for cations, okay? So if this is an olefin, and you have a substituent here, that's one substituent. Then this would be with 2 substituents, this is with 3, this is with 4. All right? So how many things are attached to this double bond here on the right? It's 1, 2, 3 things. Plus a hydrogen, right? So the hydrogen doesn't count. So there's 3 things attached to the one on the left. To the one on the right. The one on the left, you just have 2 things attached, which are no hydrogens. So that's why it's more stable. So the more things that are attached, the more alkyl groups, not hydrogen, the more alkyl groups you have attached to the double bond, the more stable it becomes. That's the rule. Like for carbocation, the same deal. Because the maximum amount of things you can have attached is 4, and then it goes down up to 0, or down to 0. All right? Other question, Isaac.
So then based on this question, like were we to see this, we wouldn't be able to tell, we would just say both can be made in some concept.
So this particular question, you just had to explain, why there's 2 products forming here, and in the other case, just 1.
Okay.
But then, this question could be extended. You know what I mean? It could be like question D, could be like, how can you now form, which one is formed preferentially with methoxide, and which one is the major one with the other, with T-butoxide, or how can you favor, the other one? These things can all be combined together, all right? Very good. I'll get you an apple maybe after, okay? Thank you, guys. Let's continue. This one. Okay, this is now different. This is arrow pushing mechanism. Who wants to try arrow pushing? Okay. Shake. Sorry. Try. So, can you guys stick around? This might take a few minutes longer than, 40. But it's an important review session. I think it's really important. Is it still recording? I think it is. Yes.
Yeah. So this is protic.
Uh-huh.
So we know it's going to be SN1 or E1.
Uh-huh. But so here's the good deal, okay? What you have to pay attention when I'm asking for an arrow pushing mechanism, right? I'm already giving you usually the products.
Yeah.
So this is good you're analyzing it, but what I'm saying is so in this case you can rule out E1 already because there's no elimination, there's no double bond formed, right? So it's just SN1 products formed. All you have to do in this case is rationalize, with the individual steps, how it's forming. You don't have to figure out what is forming, right? That would be too mean. I mean, I'll give you what is forming, what's the starting material, and I'll ask you, how does it form, okay? That's a different kind of question. There will also be these questions where I'm like, what forms, all right? Draw a mechanism, that might also be there sometimes. But if it's an easier one, this is a little bit harder, okay? Careful. So, you just said it's SN1 or E1. What you drew, the arrows you drew, basically the way you drew it is an SN2. Because you drew both arrows at the same time.
Okay.
So to show that it's an SN1, you have to draw it as 2 separate steps. I know, but this is confusing to you guys. I know, because that happens every year, and I'm like, because you think, you just draw both arrows, but it matters in which order you draw them too, okay? So you want to do it kind of like we did in lecture, exactly, right? To indicate that it's really losing the bromide first, before the next step happens, right? So you need to draw it as 2 separate things. I think that's what you meant kind of to draw, right? Probably.
Right.
But you have to, this is perfect.
Okay.
And now you can do the next step.
Okay.
If you draw it all at once to save space for time, then it indicates it's SN2. It happens at the same time. Okay? Very important. So point it right at the cation, at the carbon of the cation. You're pointing the arrow, look more on the plus sign. Point it like at the carbon. Yes, perfect. That's great.
And
now you need to draw the next thing, because it still doesn't form. Hold on. Oh. So here's the other thing. And you guys are fairly new to arrow pushing, so I'm teaching you this now. So you used OH minus. You see?
yeah.
There's no OH minus there, because I'm not giving you OH minus. What I'm giving you is water. So you have to use water. You can't use OH minus. You know what I mean? You can't just unless there's a strong base in there which would form OH minus. You have to use what I'm giving you. And then, for instance, if I'm giving you a strong acid, like a reaction, let's say in sulfuric acid or something, you can't ever have OH minus because it would immediately get protonated by the strong acid. So you know what I mean? You have to use what I'm giving you. That's the hard part. Okay? And so, sorry. So start the arrow on the O. On the lone pair of the O. Yes. Perfect.
I'm sorry.
No, this is great. This is, look, if I'm drawing it, I'll draw it automatically correct. And these are mistakes, like, because it's the first time you're doing it, okay? You make these mistakes, you learn it. That's the way it should be, okay? So this is not meant to, like, intimidate her, okay? Perfect. And now you get plus on the oxygen, right? Yes. And now there's one more step, right? Because we have to go from that to the product. We have to do the deprotonation. So in order to draw that step, you pretty much have to draw out one of the hydrogens. Let me show you. See, you can't deprotonate it like this. You have to like explicitly draw out a C. Maybe you can draw it again because I can draw it upside down. You know, you have to like draw out a CH, an OH bond. Okay? Hold on. Hold the direction. So you need now we need to take. Let's see. Let me help. Okay. I can't draw it upside down, but we will continue. So we're gonna do like this, right?
Yes.
And now we need to use a base. See, you are doing like this.
Oh yeah.
That breaks it the wrong way around. That will make H minus and O2 plus.
Right.
So we have to go the other way. Remember, always attack the H. Okay. So we're gonna. What's the base gonna be?
The BR.
The BR minus. Yes.
Yeah.
So the BR minus. So the BR minus is coming, right? And I'll make it red because I'm drawing it out. So we're gonna do like this. All right.
Okay. Yeah.
And then you get to the product. So we're going to get to the product. First one. So we're halfway done. Okay? Halfway done. Do you want to try the second one?
Quick question.
Yes.
Could an H2O come in and take that proton out?
Yes. You could either use Br minus or H2O to do that deprotonation step. Both is fine. As long as you're using things which are there. All right? And it's reasonably basic. It's fine. Both are fine. All right? Both are fine. Sorry. So now the other thing, you see the other thing there forms, and Shay's going to draw it. It forms from a rearrangement reaction, okay? Because you see what we formed there is a secondary carbocation which is not super stable, so it can rearrange. It can do a methyl shift to make the more stable. Yes, alkyl shift, a methyl shift to form a more stable carbocation. Can you draw the arrow as well for the methyl shift? So it's just like from yes, one of the methyl. Yes, exactly like this.
Okay.
Perfect.
Okay.
And then the rest is similar to what we had before. So the water comes in, gets deprotonated. Onto the carbocation. Perfect. Then we draw the next piece. So you see, you do step by step. Structure, arrow pushing. Structure, arrow pushing. Structure, arrow pushing until you arrive at the product. Okay? So these are fairly long problems because you have to sometimes draw several intermediates. But that's what it is. It's called an arrow pushing mechanism. It's like what organic chemists do like all of their life. Okay? And perfect. Perfect. Don't forget the positive charge, right? Perfect.
So small.
Yes, yes, yes. And then it's gone. Right now it's gone because now you deprotonated.
Okay.
Okay. You want 2 apples? This is hard, okay? This is the first, remember, this is the first arrow pushing mechanism you are actually writing out. I wrote you some out like this in lecture, okay? But this is the very first time you guys are doing it. So don't feel bad. This you're gonna in a couple weeks. This is gonna look fairly simple to you guys, okay? But this is the first time you're doing it, so that that takes some time. This is not a simple thing, okay? You're welcome. Thanks a lot. So, but you see, you learned a lot by watching Shay do it, okay? This is helpful because if I do it, you immediately you just see me do it, and then you will make all these mistakes. Because, why wouldn't you? Because I didn't explain it to you. Because I don't see that, you would do these mistakes. Okay, next one. Now, these are a little faster. So here you just have to judge, is it SN2, SN1, E1, E2, okay? And then just draw the product. But it's just a one-step thing. Who wants to give it a try? Or did I demotivate you guys? No. Isaac. Yeah. So then you can get 2 apples in here. All right. So analyze it somewhat, right? You can keep talking when you do it.
If it's cyanide and DMSO.
And the primary alkyl halide.
And a primary alkyl halide, it's going to be SN2.
Yes, absolutely. Why? Because cyanide, remember in lecture I told you, is a great nucleophile. So that speaks for SN2. DMSO, a wonderful example of a, polar aprotic solvent, right, which is great for SN2, as I said in lecture. And then a primary alkyl halide, non-hindered, great leaving group. It's a great substrate for SN2. So everything speaks for SN2 here, right?
And then
so you do the SN2 and then you just draw the product. So maybe write SN2 on the line, right? That's what I'm asking for. Curved arrows. Yeah, that's great.
And it comes in from the back.
It comes in from the back, but it doesn't matter here because it's not the chiral center, so it doesn't even matter. So it's really good. It's a simple problem, okay? But you did a wonderful job doing it, okay? Thank you. So who wants to try the next one? Do you guys have any questions about this one? So just pay attention to all these signs. Solvent, what's the alkyl halide? Again, on Friday, I'm going to give you a table, which helps as well, okay? I think Aubrey gave you, or she said she will give you a flow chart as well, how you can decide. So solvent, the type of the substrate, the type of leaving group, the type of nucleophile or base you have, okay? That's what matters. You'll be able to figure it out when you do problems. So let's do the next one. This one. What do you guys think? It's an elimination, yeah? Do you think it's E1 or E2?
I think it's the base, because the base is bulky.
Medium bulky. Ethoxide is not very bulky, but it's a pretty strong base. Okay? Whenever you have a strong base, the base will actively participate in eliminating, and so it's E2. Okay? If you don't have a strong base and it's eliminating, then it's usually an E1 mechanism. Okay? So this will be more like E2, and I'll draw the mechanism for once. Let's see. Okay. So, yes, so then it basically takes off this proton here, like this. Okay? Now, this could be a trick question, okay? I took this from one of my colleagues. So to make sure it's not a trick question, you have to make sure, because sometimes this is a secondary substrate, okay? to make sure it's not a trick question, it's better to draw out the chair, make sure that, you know, that the thing we are taking off, the proton, can be aligned anti-periplanar. So it's really, otherwise E2 is not possible, right? So I'll just draw you guys the chair here, like we've done before. This would be the chair. Let's say, then the iodide has to be in a axial position in order to eliminate, right? The methyl then here is pointing up, and the equatorial hydrogen is pointing down, and you see how beautiful this is aligned here, anti-periplanar, okay? So this is absolutely E2, all right? So again, the mechanism here is OET minus, right? We have these 3 lone pairs, and I'll draw it in red, so it's taking off this proton and making the double bond here, all right? Good? So that's an E2, and you see it fits with the chair thing, okay? So, and that's why the methyl group is there, because it locks it down in this conformation where the iodide is axial, actually. That helps the reaction. Shay?
Doesn't protic solvent do anything?
A protic solvent, in this case, it's, I said it's not ideal for E2 reactions, but in this case it's fine, because the reason it's that people use ethanol is because they're using ethoxide with it, okay? So that's because, you know, ethoxide is the conjugate base of ethanol, and it's nicely soluble in ethanol. So the way you make ethoxide in ethanol is you just take ethanol, when you add like sodium or something, and that makes a bunch of ethoxide in ethanol, and it's a beautiful solution, and you can use it, okay? That's why it's used. So it's not ideal. You could do this also you could use ethoxide in DMSO. That'll be fine. Or ethoxide in DMF. That would also work, all right? So sometimes the solvent doesn't fit perfectly for the mechanism you're doing, but that's okay, as long as everything else more or less fits, all right? It's a good question.
So why is it that you checked if it's anti-periplanar?
So if it were not anti-periplanar, then maybe something could happen too as an E1 process. Sometimes, but not in this case. I will try not to give you too difficult of things to do.
Okay. So
If I want you to, sorry?
How would we recognize that? Like, how do you know to check this one specifically? Just because it was E2, or?
I just wanted to check.
Oh, okay.
And I wanted you to go through the thought again. I knew that it was okay.
Okay.
I just wanted to make sure that we can go through the chair thing again, and it really all fits together.
Gotcha. Okay.
There could be examples, like, I can give you an example where, for example, it really can't flip, okay? Where you pretty much can't do an E2 process. And that's, for example, you know, with a decalin system, like if you have 2 fused rings, right? If you have a thing like this, we've seen that, if you have something like this. So now if you put the iodide here, then this cannot do a chair flip, right? Because it just can't, it never can, it's impossible. So then in this case, you can never put the iodide axial, and then it might be really difficult to do an E2 mechanism. So then if it still eliminates, it might do it through an E1 mechanism instead, all right? So, but not in the other case. So don't worry about that, all right? For now. But it's good. You have to be able to draw the chair, you know, do the elimination like we've done before. All right? Few more here. How about this one? What do you guys think? Let's do it together. I will keep doing the drawing now, okay? So we move forward. We'll still be here like 10 o'clock. Maybe not. We did the hard ones already. So what's this? What do you guys think? SN1, SN2. Is it a substitution or an elimination? Substitution. So it's an S. N. Now the only question is it 1 or 2? 2. Because sulfur is a great nucleophile. Right? Great nucleophile. So that's why it's SN2. All right? Whenever you see SH minus or something, that's a great nucleophile. So what happens in terms of mechanism? Again, you get backside attack, but it doesn't matter because it's not a chiral center. You kick this out. Done. Sorry. Can you guys see it? Okay? That's it. Next one. You guys good? This one. How about this one? Oh, you don't know what a tosylate is. Sorry. Tosylate is this thing. So OTS is an abbreviation. We're going to learn about it on Friday.
it looks like this. It's this thing like this. That's why it's abbreviated, because it's pretty big. That's a tosylate, okay? That's fine. I would draw it for you like this. So what's happening is it behaves like an alkyl halide. Why? Because this thing here, if you make an O minus, it's like sulfuric acid. Very similar to sulfuric acid. So it makes a resonance stabilized anion when it leaves. So it's a great leaving group. All right? So this thing basically leaves. Okay? The tosylate leaves. And the NH3, that's ammonia, that's a nucleophile. All right? That's a solvent. So what do you think happens here? Is it an elimination reaction? No, because no double bond is formed. So it's a substitution reaction, okay? So it's again SN. The question is 1 or 2. And why? 1. Yes, why? Because it's what kind of thing is this? It's a tertiary tosylate or a tertiary leaving group, like a tertiary carbon atom, okay? And so that can never do an SN2 reaction. As I said, it's too sterically hindered. And besides, you see that it would have to, the nucleophile would have to attack from the back side, and the back side is completely enclosed by all this other stuff here in the back. So there's no way it can attack from the back. We have to go through the molecule somehow. It doesn't work, okay? So that means the mechanism is SN1, all right? Because we have a tertiary substrate, all right? So now, what's the mechanism? Like before, leaving group goes away. You form tosylate, which is it's a tosyl anion, and then you get a carbocation, tertiary carbocation. All right? And then what's next? Like before, now the ammonia is coming in as the nucleophile. The same thing we had before with water, right? So this is the arrow pushing mechanism. You get to this thing. Da-da. And now it's NH3. Now we have a plus on here, right? And then finally we have to deprotonate it. So ammonia will act as the base. And again, like before, we have to write it, in order to draw this step, we have to write it as NH2H. Right? Otherwise we can't deprotonate it, we can't draw the arrows. Like before, same deal. And you do like this. You get to the product. Make sense? Any questions? You guys are good? So then we go to the next one. Okay? Next one. Another one. SN1, SN2, E1, E2. Again, it's a tosylate, like before, right? Leaving group. Substitution, so it's an SN. Primary, which is heavily leaning, right, toward 2, right? And that's it. And then look at what's the solvent? Acetone, polar, right? A product, again, SN leaning toward everything. All the signs are pointing SN2, okay? And what about the nucleophile? Br minus is a pretty good nucleophile. It's also good for SN2, okay? So what happens is SN2, you draw the mechanism, take the lone pair on the bromide, do like this, done. Okay? Any questions about this one? So you look at the signs, whether it's SN1, SN2, we're done. We're almost done. All right? I think there's like 1 or 2 more questions. Yes?
I have a question. Are these both the same configuration, even though it's SN2?
So yeah, the question is, look, very good question. Configuration, look at these carbons here. We didn't change the configuration, right? And I said there's a change of configuration. That's because the change of configuration happens at the alpha carbon. This is the beta carbon. You see that? So this is the alpha carbon, but the alpha carbon here is not chiral. Right? And that's from the back side of the alpha carbon. That's where the nucleophile, the Br minus, comes in. The beta carbon here is chiral, but we are not changing the beta carbon. We're not touching the beta carbon, so it stays the same. It's a wonderful question. Does it make sense?
Yeah.
That's why. All right? And why am I putting these things there? To see if you got the... So this one, what's the rate determining step of an E1 mechanism? Formation of the carbocation. All right? Of the carbocation. We can also say AKA loss of the leaving group, right? LG, leaving group, okay? All right, that was a simple one. Next one. Now, is this I think this is the last one. No? How many more? 5 more? Okay, fine. We'll continue. These are pretty quick. We'll get through it. For each reaction below, indicate the products whether the reaction is SN1 or SN2. So no elimination, right? And we need to draw the products. So what are the signs? Primary. SN2 leaning, okay? Cyanide. Great nucleophile. SN2. Ethanol, again, the solvent, this is polar protic, but it can still be used as an SN2 reaction sometimes. So SN2, right? This is SN2. Now what happens is the cyanide, let me just draw it like this. We say Cn minus, right? That's the nucleophile, kicks out the bromide, and you draw the product, which looks like this. Does that make sense? Those are not as hard as the beginning ones. So I'm going to flash forward to the next one. Here. SN2, SN1. Substrate, sorry, what is it? Secondary, primary, tertiary? Secondary, right? That's why I said secondary first. DMSO as the solvent, polar aprotic, that speaks towards SN2. Br minus is the nucleophile, again, good nucleophile, SN2, right? And so that's going to be SN2. Backside attack. So from the back, right, that's always in SN2, from the back of the carbon-chlorine bond, that means where does the bromine end up? On the back, okay? So we get inversion of configuration. Oh, hold on. Oh, this is a tricky one. Sorry, guys. This is a tricky one. So now, because you see there's another chlorine. You see that? And now, so let's take off what I already wrote. This is a trick one. I took this from my colleague. He put these things on the exam last year, or 2 years ago. Not Sandy. Okay, and the average was literally like a 50, or maybe a 60. It was a hard exam. Okay, my exam, you will see that the practice exam is online. It's not as hard. All right, these are much harder than the exam. I might make the exam a tiny bit harder than last year's, but it will be fine. Or maybe not, all right? But look at this. This is a tricky question because there's 2 carbon-chlorine bonds. And the question is which one reacts preferentially in an SN2 reaction, because one equivalent means you're just adding one equivalent, 1 mole, right, of Br minus. That means it's not enough to react with both. If you add excess, you know what I mean? So which one do you think reacts faster in an SN1, SN2 reaction? Is it the primary one on the left or the secondary one in the middle? The primary one, right? And we had this in lecture because it's less sterically hindered and so it goes faster. So actually what happens is you react with the primary one. So you have Br minus, which again it always attacks from the backside, but here it doesn't matter because it's not a chiral center. And so, bless you, so what you get is mostly, not exclusively, but mostly this guy. Okay? So you see that's a really tricky question. Okay? But you follow the reasoning, okay?
But is the chlorine still, the second chlorine is still attached to that product?
Oh, yes, absolutely. Oh. Sorry, I forgot to draw it because I'm starting to get tired after 75 minutes. Okay, let's move on. Okay, one more. Indicate the products, whether the reaction is SN1 or SN2. What about this one? This is a tertiary one. Never SN2, so it must be SN1, okay? That's the only option left. So, again, the mechanism is you lose the Br minus first, loss of the leaving group, make the carbocation, and then you get the product, which looks like this. as OCH3. Okay? Now, the thing is it's still chiral. It's still a chiral center here, you see? But it goes through a flat carbocation, so you can make both products. You can make the R and the S. So we'll say it's about 1-to-1 mixture of R and S, right? This AKA racemic. I'll show you on Friday how this goes. It's essentially you get to this, the intermediate, right? It's not hard to understand. The intermediate is flat, all right? That's the intermediate you form here. And now, what can happen is, the methanol can come in from the front. OCH3, H, right? So this would be the methanol coming from the front, all right? That gives you one of the products, either the R or the S. You can figure it out, right? And then if the methanol is coming from the back, if it's coming from the back, it gives you the other product, right? So there's no reason it would preferentially come from the front or the back. The two sides are equivalent, so that's why you get a 1-to-1 mixture of R and S. All right, I'll go for this again on Friday. Questions? Yes. Oh, the two sides are not, they are the same. Because you see, symmetrically they are the same. The whole thing is flat. The carbocation is sp2 hybridized. Well, initially it's not the same because you have a chiral center. But once you lose the Br minus, it becomes flat. It becomes all flat, okay? And then it's just a plane. And the plane can be, remember the methanol is just swimming around everywhere in solution. It's swimming around on top and at the bottom. So sometimes randomly it comes from the bottom, sometimes randomly it comes from the top. The chance that it comes from the bottom and the top is exactly the same. And this is why you form both products, the R and the S, in the equal ratio, more or less. Does it make sense?
Yes.
That's what happens. You have to digest it. That's another thing. Okay? So, all right. Caroline.
Just really quick, do we have to show both of the wedge and dash versions, or can we just do that instead of
You could do this and you can say both isomers. The other thing you can draw it is literally like this. You can just like do this. You can draw like this guy, OCH3 plus, hold on, I think I lost, this must be another one, right? You can literally do it like this and write both of them. That'll be fine. Or the other way you can do it is you can write one of them and then write plus enantiomer. That's also fine, okay? As long as you indicate that both can form, that's fine. And frankly speaking, they don't always form as a 1-to-1 mixture. Sometimes it inverts the stereochemistry more than it racemizes. So that happens, all right?
So don't try that. Don't put 1-to-1. Just either do.
But you can put 1-to-1. I won't care. I can't predict it either.
Okay, cool.
It's essentially as long as you know that both can form, that's fine. So if you just draw me one of them and you don't draw the enantiomer, I might take off like a point, or you don't indicate that that the other one can form. Generally, it's not, as long as you understand that the other one can form, you don't forget about it, you somehow indicate it, you should get the points. All right? So then, yes, Shay?
The water deprotonates the methanol.
Yeah, the water deprotonates the methanol. Oh, yeah. Frankly speaking, also the water could also react, and make another product. But we won't worry about it. Let's change this. This would be better to do in methanol, just in methanol, okay? The water can make other products as well, and then it gets even more complicated. Because the water can react equally to the methanol, then you make an alcohol. And then it's even worse, okay? So you wouldn't want to do this with water and methanol mixture, generally. We just use methanol. I think it's just a mistake on the problem here. All right, let's see. Now we just need to know what reagents and solvent we want to use. That's pretty quick, okay? Then we're done. So, first one, what would you use? You would want to use an SN2 reaction, right? Because putting a CN group comes from a CN minus, right? The cyanide, like we have seen before. So this would be something like sodium cyanide. Now, if it's an SN2 reaction, what solvent would you want to use? Something like polar aprotic, right? DMSO or DMF or something like that, okay? So you put like DMF over here. Done. Done. All the points, okay? Next one. This one. What about this one? This is a little... Yeah, this is like the one you did in lab, okay? You have to see that OH is a really... OH minus is a really terrible leaving group, right? So what did you do in lab? You added sulfuric acid, right? And then this one goes through a SN1 mechanism. So if you add sulfuric acid, that will protonate the alcohol and that becomes water as a leaving group. So you form the cation. Now you need to trap the cation. You need to react the cation with Br minus, right? Or Br or HBr in order to get it to substitute. Makes sense? So you have to add something like, you have to add Br minus as well. So something like sodium bromide. Okay? That's how you can do it. Okay? Last one. Are you guys good with this one? These are all pretty tricky ones, I must admit. This is a little bit easier. What can you do here? You guys tell me. It's SN2, yes? Because we put in sulfur there, and that's good nucleophile. What nucleophile would you want to use? What reagent?
No. Something with an S.
With an S minus.
Yeah.
Not sulfuric acid. Sulfuric acid doesn't have an H. Sulfuric acid looks like this. That's sulfuric acid. You see, it doesn't have an S minus. It just has an O minus. Okay, very different. You don't want to use sulfuric acid. Sodium SH, exactly. Sodium SH, that's SH minus, all right? We've seen it before. That's what you want to use. So now here's the question. Doesn't that invert the configuration? Because it comes from the backside. Yeah, that's right. So you invert the configuration, but it's not a chiral center because it's not a chiral center. It has a mirror plane. Okay? So that's fine. All right, but the way it's drawn, it looks like we inverted the configuration, but it's the same as if we turn the molecule upside down. All right, Isaac, last question.
When you write it on the bottom like that, like the sodium SH, is that the reagent or is that the solvent?
That's the reagent. You're right. We forgot to add the solvent. So if you forget to add the solvent, like I would take off a point from myself here. So what solvent would you use?
Would it be polar aprotic?
Polar aprotic. So for example,
DMSO.
DMSO would be perfect.
But does it matter what side of the arrow you write?
No.
No? Okay.
No, generally, so here's what I would do probably, okay? If I ask you something like this, I will not let you just write stuff randomly. Because otherwise you forget to add the solvent. Or you forget to add the reagent or something. So what I will do is I will probably give you a box, or I will be like, I would use this solvent for the reaction. You know, like the solvent, and you put it in that box. You know, and then the box for the... So it's easier to grade and it's clear. All right? Just make sure you answer everything. So what you need to do, pick up some apples, okay? I don't want to bring them all home if possible. I have hundreds of them, no 50 or so at home. Pick up some apples and then study this stuff. Okay, it's really hard. It is really hard material. Okay, I'm sorry about it, but it's just hard. All right, we're gonna keep practicing and do more stuff in lecture too. Okay, thank you for coming.